Chapter 16 will discuss waves and sound. Some important questions we will cover in this video are: what are waves and what are their characteristics? What are some different types of waves? How fast do they move? And as well, what is the Doppler effect? First, looking at a wave from Friday, you saw a wave is a traveling disturbance that's going to carry energy from place to place. It specifically transmits energy through matter or space, where the medium is the matter through which a wave travels. Some examples are air, water, and ground. Sound, for example, can travel through all three of these mediums. You can see the effects of waves, or what waves look like, if you see a rock being thrown into a pond. When you have this, you'll create a disturbance that travels out. The shape is going to be a circular path. And the important thing here is that the medium is not displaced, only the energy. As the wave moves out in a circle, the energy is spread out over a larger area, creating smaller and smaller ripples. Two specific types of waves that we will be describing are electromagnetic waves and mechanical waves. All the waves we're going to deal with right now are mechanical, meaning the fact that they have to have a medium through which to travel. For instance, sound, again, has to have a medium. So when you get into a place like space, you are not able to have sound. So if you've ever seen Star Wars and seen the explosion of the Death Star, the sound of that explosion should not have happened because of the fact that there's no medium for which to propagate the sound wave. We'll then later look at electromagnetic waves, which require electric and magnetic fields that we've discussed previously. Two other types of waves that will both fall under the category of mechanical are first transverse and longitudinal. Transverse waves were shown in the PhET simulation that we saw the other day, and a longitudinal wave can also be shown. However, unlike the PhET simulation, a longitudinal wave will be a back and forth motion that is along the same direction the wave is going to travel. Based on a transverse wave to start with, the particles of the medium are going to move or vibrate perpendicular to the direction of energy propagation. And so, for example, in this drawing here, the energy is going to be moving towards the right across the screen, while the particle here moves up and down. So the particles move perpendicular to the energy. Longitudinal waves are very easily shown using a slinky. If you think about each of these lines as the coils of a slinky, we can connect them all using diagonal lines, and then we can see the shape of that slinky as it moves through. There are two spots where the slinky coils get closer together, and those are going to be known as compressions. These compressions then also lead to areas where you have less space, and those will be known as rarefactions. In a longitudinal wave, then, the particles of the medium vibrate parallel to the direction of the energy propagation, where our energy is, again, moving to the right. Both of these types of waves, both longitudinal and transverse, when repeating through multiple cycles, are periodic waves. Every time you then have the slinky moving up and down, or a wave moving up and down, or compressing and stretching in a longitudinal, will indicate a periodic motion. Looking at these waves, there are four characteristics that we're really going to focus on. One cycle being shown in the shaded area. The amplitude is going to be the maximum particle distance from its initial or undisplaced position. The wavelength then is going to be the horizontal length of one complete cycle of a wave. We'll diagram that later. The period is the time required to complete one cycle, and the frequency is related to the period by equation we learned before, that frequency is 1 over the period. As far as the units, frequency is measured in hertz, period is measured in seconds, wavelength is measured in meters, and amplitude oftentimes is measured in meters, but can be also sound pressure depending on the type of wave you're looking at. To diagram out these important spots and two other terms, we have a diagram here of a wave. We'll first start with the amplitude. The amplitude of a wave can be shown as the distance from the undisplaced position. So that can be shown here as well as this spot here. And so both of these are the amplitude of the wave, and it's always measured from the 0 position, so both an up and a down component to that. Those spots where we are reaching the top and the bottom are known as the crest and the trough. So the crest will be any point where we reach a maximum on our wave, while the trough will be any position that is the bottom of our wave. And there's one more over here. The wavelength can then be shown as the distance between two identical points on a wave. An easy way to think about that is crest to crest and also trough to trough. We can see another position here in the center where I'm going from one position to the other. However, when we check the instantaneous slope of this line, you'll note that they happen to have slopes that are not the same. Because of the fact that the slope is not the same of my line, I have not reached a full wavelength. And so I'm going to come back and go all the way when I'm at my equilibrium position, not one, but two positions. At that point, my slopes are the same of my line. And when I look at these lines all together, all of these wavelengths are roughly the same value. It was slightly different because this was hand-drawn. The symbol for the wavelength is going to be the Greek letter lambda, which looks like an upside-down Y. As far as then relating these, we can use our distance formula, or our constant speed formula, to figure out the speed of a wave. The speed of a wave is dependent on the distance it travels and the amount of time it takes. The period defines the time it takes for one wavelength to pass. And so we can get an equation for the wave speed as the wavelength divided by the period, or that the wave speed is equal to the frequency times the wavelength. This can also be rearranged, and we'll use this to solve a problem with AM and FM radio waves. These two waves are detected by your antenna on the car and can detect waves with a speed of 3 × 10⁸ meters per second, also known as the speed of light. AM radio waves and FM radio waves differ in their frequency, and even though they have the same speed, will have different wavelength as a response to that. The distance can then be calculated using our formula. For AM frequencies, the wavelength is going to be 244 meters, while for FM, the wavelength is only 3.26 meters. Going back then, the AM radio wave has a larger wavelength, while the FM wave has a larger frequency. The speed of sound, or the speed of most waves, is going to be dependent on the material or medium that you pass it through. For the speed of sound, it's roughly about 343 meters per second is the standard temperature and pressure speed of sound. However, as we go from gases to liquids, you'll see usually an increase, and from there to solids an even greater increase. And this has to do with the distance between the molecules inside of the medium. Going back to our longitudinal waves, then this is a great way to represent a sound wave. Sound waves are going to be longitudinal, and it comes from the fact that there is air pressure, and as the particles in a sound wave move along, the air molecules get closer together to form a compression, and further apart to form a rarefaction. Down here you can see the rarefaction, the compression, and what a normal air pressure would be. And so you create a sound wave by having the air molecules get compressed and expanded away from each other. The wavelength then can be defined as the distance between the two compressions or the two rarefactions. However, this is difficult to represent in a graph form, and so what we can do is take this longitudinal wave, and by looking at the air pressure, we can take it and apply it to a graph that forms a transverse wave, where the amplitude again is the height from our zero or our normal air pressure. We have troughs and crests, rarefactions and condensations or compressions, and the wavelength is the distance between our two compressions. The last topic here is the Doppler effect, and that's going to show what happens to a wave when we have an object that's moving. For everything we've looked at so far, the source of the wave was at a constant position. The Doppler effect takes care of what happens if an object, a source, or an observer is moving to the wave itself. Up at the top there in the first graph, you can see that when you have an object like a fire truck at rest, it creates waves that go out in a circular pattern. The waves then hit the two observers, one in the back and one in the front, at the same wavelength. Because of that, everybody hears the same frequency. However, when the truck is moving, you get a different thing that is happening. The source is now moving, and so this causes a compression of the waves in front to create a smaller wavelength and a larger wavelength in the back as the source moves away. A smaller wavelength from our wave speed equation is going to indicate the fact that we have a higher frequency that is heard, and a larger wavelength indicates a lower frequency. And so there's an inverse relationship between the two of those. We can then calculate the observed frequency depending on whether a source is moving or not based on some equations. For a moving source, when the truck is at rest, we have a certain wavelength, but as the truck moves, it decreases the wavelength of the frequency heard by our observer. And so whenever a truck is moving towards an object, or whenever a source is moving towards an object, it will actually increase the frequency of the sound heard. If an observer is moving as well, you can get the same effect. And so an observer still moving towards the source is going to also increase the frequency that is heard by the observer. The general equation for this can be shown here, where the observed frequency that is heard is equal to the source frequency, which does not change whether or not the object is moving, times an equation here, where VO is the speed of the observer, VS is the speed of the source, and V is just the speed of sound in air. And so these V's are constant, normally 343. This equation can then be simplified when you have an object that is either an observer that's at rest or a source that is at rest. And so as a quick plug-in of this, we can look at a passing train and the speed heard. And so a train is moving at 44.7 meters per second. This is our source speed, or VS. 415 hertz is the source frequency, or FS, and the speed of sound is 343. That's just V. The question then asks, what happens to the frequency observed when the train is approaching versus when it is leaving? The two equations can then be created from down here. And so if it's approaching from before, that should indicate an increase in frequency, and leaving would be a decrease in frequency. We can see that for approaching, you get 477 hertz, which is greater than 415, and leaving, it gets to 367, which is lower than the initial of 415. If you're moving with a stationary source and a moving observer, you can get these two equations as well to plug in. But all that it really is the effect that we're looking at as objects, as the source and observer get closer together, the frequency increases. As they get further apart, the observed frequency decreases. Some applications of this then are ultrasound. So ultrasounds use ultrasonic waves, which are above what humans can hear, and by looking at the distance and objects that are moving, they can take a look and create pictures based off of this. This is also important when you have moving objects. They have to take into account the Doppler effect. You can look at actually the flow of blood using a special device, and by looking at knowing the speed or the difference in the incident sound, the frequency of it versus the reflected one, you can figure out how quickly blood is flowing through a vein. To finish up then today, I have a few questions, some multiple choice. I'll leave these up. You can pause them and try them on your own, but you'll see the answers as well. And pause.